right, the next speaker is Thomas Bögl from Rohde & Schwarz. And we have the slide already on the screen. As with all those previous talks, we're dealing with bloody edge, we're dealing with maximum performance, questions maximum throughput, maximum, all maximum, you know, we're going to the limits. And we've never had this topic in the past. We're pushing limits, yeah. We've never had this topic in the past. How far can we go? How fast can we go? And one of the most important components is analog digital converters and digital analog converters. And so I asked Thomas to give us an overview where the industry stands, and particularly not, well, we have a speaker from Analog Devices later, but I wanted to have a talk from somebody who's making a choice which devices need to be brought into a project. And Thomas is doing this on a regular basis as an engineer from Rohde & Schwarz, and so he's a perfect speaker for particularly this topic. Please give a warm welcome to Thomas Bögl.
Thank you very much. First, a few words to the audience here. You see Tommy Valten, who is a colleague of mine. Tommy and me, we are working together for almost 40 years, making different kind of radios. Tommy has today a much higher priority than software-defined radio because his wife is celebrating birthday right now. So greetings to Helga and to Tommy, and then let's start. So it's quite often the case that I'm going to Tommy and ask him, I want to create a new software-defined radio. What kind of analog digital converters do you provide to me? What kind of signal processing stuff can I get? Or the other way around, that he's coming to me and says, there are new devices on the market, new signal processing algorithm, whatever. What can I do with that? And just in advance, what we are doing right now in the next few slides, we are building a software-defined radio receiver together with an instantaneous bandwidth of 5 gigahertz, and just see where we are ending, okay? But anyway, independent on the question you're asking about the architecture, you must know the architecture, you must know where the converters are and how they are harmonizing and are being part of the overall architecture. So allow me a few slides, exactly 2-1, just to check the architectures around the converters. Now we are starting with the receive side, and I have here 3 basic architectures of a software-defined radio receiver. So on the top, we have that one everybody wants to build, which says it's an A to D converter more or less directly at the antenna. It's the basis for the highest instantaneous bandwidth, but has some challenges for the A to D converters. The second one is a superhead concept, which means between the antenna on the left side and the A to D converter, there's a mixing process in between. And the reason why we are doing this is just getting rid of very strong interferers. That's the only reason for doing that. And the third concept is a zero IF concept, which says we are mixing down right from the antenna down to the baseband. I and Q, we saw from Michael's presentation the complex numbers. They are appearing already in very early stage in a hardware block diagram already, representing cosine and sine. And if we are now looking to the challenges for the converters, so the first concept is the most challenging one for the converters. So it could mean that you have a plan to build a radio with that block diagram that you won't find any converter at all to fulfill your requirements on the antenna interface, which is the reason why I wrote down up to unsolvable. May happen. So compromises are required. In the middle and below, you have something in between the antenna and the converters, which depends now on the compromise you're finding. But the challenges for the converters are significantly going down. And that's very important, but you're losing something. You're losing bandwidth or whatever. And so zero IF is more or less the same. They are different in hardware costs, in performance. Zero IF, for instance, is not the best if you want to operate purely analog modulation schemes in some applications, like in air traffic control, where I'm living in. But basically, the lowest two are comparable with an effect on the challenges for the converters. Now we're turning the direction opposite way around and make a transmitter. The concepts are basically the same. The top block diagram is just digital to analog converter directly at the antenna. And the other tools are the other way around, a superhead concept, which means that digital to analog converter is operating on an intermediate frequency, and then we are mixing this frequency up into the final frequency range our radio is operating. Or zero IF could mean you have an analog IQ modulator cell. You're taking two baseband digital to analog converters and just modulating the complex modulation on top of an unmodulated carrier right on the final frequency. There are some analog components which can do that. Now let's look to the main companies you can get devices. If you are looking to the challenges and the most modern technologies with respect to sampling rate, dynamic range, and all these things, you will find significantly higher number of companies providing converters. But these three from our daily business are the main companies which are appearing on our desk. So AMD, Texas Instruments, and Analog Devices. I have 3 slides for each company, 1 slide, and we must be aware that when we are going up to the higher gigahertz sampling rates, it's not just sufficient to have a converter as a device. You must have a circuit around which is able to work with these damn high frequencies. So that means in many cases you are not buying the converter itself, you are buying the converter as a part of a system on a chip. Which means you have the converter surrounded by more circuits like digital up converters, digital down converters, clock PLLs, and whatever. Otherwise, you won't be able to do anything at all with the samples coming out from the device. So when we are talking about an analog to digital converter or digital to analog converters, we are normally talking about quite big chips with extremely fast hardware blocks which can be configured to represent your individual signal processing block diagram. And you see here some really astonishing figures. So sampling rates, 2-digit gigahertz sampling rates are quite normal. So 32 giga samples per second. Output frequencies at the antenna level of 18 gigahertz is possible. The question is it good for your design? Is it good for your application? If you're looking to Texas Instruments, the situation is quite similar. You have really a lot of devices with 10 gigahertz, 12, 20 gigahertz sampling rates, high resolution. They are competitors, so they are competing with each other to provide the best devices for the markets. And finally, Analog Devices, also a company which is not only providing this kind of circuits, also a lot of analog circuits, which are part of the overall block diagram of the complete radio. So you can have up converters, down converters on the analog domain, modulators, demodulators, all this stuff, and these system on chip devices with extremely high sampling rates and all the associated circuitries around. Now we go into more detail and we are picking out the top block diagram of a software-defined radio receiver we saw a few slides before with the A to D converter on the antenna. This is our focus now for the next few minutes. And what's of importance is the dynamic range, which means what is the minimum signal I still can see, what is the maximum signal I can apply without saturating the A to D converter, and what kind of noise am I picking up, which is also the limit for the sensitivity of these devices. So this block diagram is very similar to the previous one. This is from Tommy. The other one was mine. So we have a co-production here in this presentation. So we did not make some optical work. We just put in what we have. So we have the analog signal processing, which is in our case gain or attenuation. We say we have an anti-aliasing filter in that, but we do not have any other filters limiting our operational bandwidth. That's the key of the block diagram. Then we have the analog to digital converter, and we have a digital signal processing working with the samples coming out of that device. Now two pictures, one for A to D converters, the other one for digital to analog converters. So we have the A to D converter on the left side. We can get out already complex numbers with the samples, cosine, sine, and here we have some typical processing blocks. And one is a decimation filter. The purpose is mainly to get these damn fast sampling rates down to a speed where I can work, for instance, with software in a classical processor. Then we have filters like this FRR filters, any other filters. But the first step is very often just to get the sample rates down. And in this down conversion process, make already some algorithmic work. That's the key. The same for the up conversion. So if we have an extremely high output frequency, we must up convert what we have on the baseband domain for our waveforms up to the sampling domain close to the antenna and close to the devices. And now we are starting to build up a receiver. So this is one picture of many pictures characterizing an A to D converter. First of all, we must be aware there's a maximum input level allowed without saturizing the device. This is very important. Then we have here some noise, which is kind of the quality of the device, like the noise figure of a receiver. And on top, we have the noise we are collecting with the processing bandwidths we are operating the device. So we are picking up a lot of thermal noise. And what we are basically doing with all the signal processing algorithms, we are starting on top with the maximum allowed level, and we are diving down into the noise. That's what we are doing. Now you might have a question, how can I dive into the noise beyond the resolution of the A to D converter? And I just give you a very simple example. Let's say you have an A to D converter with 2-bit resolution, not more. We have 4 states, 0, 1, 2, and 3. Now let's assume we are building a voltmeter, just measuring 1 volt, 2 volts, 3 volts. What happens if you are applying 1.5 volts? Exactly in the middle between 1 and 2. And if the A to D converter is a quite precise one, it will toggle. It will toggle between 1 and 2. And if we are, let me say, exact in the middle, and we have an A to D converter with is exact 1 and exact 2, then you can count the samples and make the average. And you will see, you will get an average of half of the time providing 2, and the other half of the time providing 1, which is an average 1.5. So that means you're paying time, but you're getting resolution. It's just averaging. So now you have a build with 10 averages. You have built an analog to digital converter with 10 times higher resolution, having only 2 bits, not more. So that's the basic principle behind. And now let's start to build a receiver. Don't worry, I will only pick out a few of these values just to understand what's going on. And in the next slide, we see then the block diagram representing these figures. So we take a data sheet, analog devices 9213. It's a 12-bit A to D converter capable of being operated with 10 gigasamples per second. Then we know from the data sheet we can apply maximum +7 dBm peak power at the input, which is represented by a differential input with 1.4 volt peak in a 50 ohm load. The manufacturer says we have a signal to noise ratio of 55 dB with that device, and now we are building a receiver which is going to the Nyquist frequency, just half of the clock frequency, which is the 5 gigahertz here. And now we are collecting the data, which is dynamic range, noise, and all these things. First, we have to look to the 5 gigahertz bandwidth. We are picking up natural noise floor. And this is the next one here. So the thermal noise floor at room temperature is minus 174 dBm per hertz bandwidth. So that means if I'm building a power meter as a receiver with 1 hertz bandwidth, it will give you a reading of minus 174 dBm. If I'm increasing the measurement bandwidth to 10 hertz, which is 10 dB more, then you will get an absolute reading of minus 164. And this is what we are doing. We are just picking up natural noise in the processing bandwidth. So that means if we go to 1 kilohertz, we have 30 dB, 1 megahertz, 60 dB, 1 gigahertz, 90 dB, 5 gigahertz is 97. So this is the figure. So keep this 97 in mind. It will appear also on the next slides. What we are now doing, we are coming from the plus 7 dBm, going down what the manufacturer says is our dynamic range of our signal to noise ratio of our converter. And then we are adding the absolute noise power. And the limit we are now reaching is that noise, which is our absolute limit for the device. We cannot go lower, which is in this calculation example 29 dB. So it means if you put this device directly to the antenna without any attenuation in between, no gain, you will have a receiver with a noise figure of 29 dB, which is on HF not so much if you go to the lower frequencies. If you want to build this as a VHF or UHF receiver, it's a horror. It's an extremely bad data sheet. What we now doing, we are playing with bandwidths and gain, just to optimize our design. And now we are building the receiver. We have only one component now in our block diagram, which is a low noise amplifier, nothing else, because we want to improve the noise factor, which is normally a question of gain at the front end. So we have a noise factor for the LNA, we have a gain for the LNA, now we have the situation again. Now we have here the minus 174 dBm per hertz is our minimum thermal noise floor. We have here our 29 dB noise factor from the A to D converter. Everything on top is just collecting based on the bandwidth, which is, by the way, minus 145 dBm. Now, the low noise amplifier, let's say we have, in this example, 4 dB noise factor, which means we have a amplifier without any noise and a noise of 4 dB higher than the thermal noise floor at the input, which is minus 170 dBm. Now the amplifier is doing some gain. In this example, I've selected 24 dB gain, which means we will have minus 146 dBm per hertz noise floor density. And if you compare this with the 145, it's roughly the same, which means if you are putting this combination together, you will have a receiver which has 3 dB more noise factor than the front end. Because at the end, you have an additional contribution of noise, which is exactly the same as you get from the front end amplified with a low noise amplifier. And now, what about this one with the maximum level? Now we are going down, which says our data sheet said, please not more than plus 7 dBm. Now we have to go down with the gain. And this is the maximum level we can apply at the input. Otherwise, our device is saturated. That means now we have a receiver without any preselector. We are just talking about an ultra broadband receiver with 5 GHz instantaneous bandwidth. And the maximum interferer level you can apply is minus 17 dBm. Now we have to take into account, if you put an ultra broadband receiver to an antenna, it will pick up a huge amount of spectrum, a lot of signals which are added up. So that means we are not talking about a single carrier with a minus 17 dBm. It's superposition of all the voltages on the antenna, and the amount of adding different signals is huge on the antenna level. So it's not so easy. In that case, normally we would say, okay, probably have to insert a filter already, forgetting the 5 GHz bandwidth. So we are playing again with bandwidth and gain and so on. So what we are now doing, we are reducing the signal processing bandwidth, which means we are reducing the bandwidth here. And this is representing with the 5 GHz is this area here. So we have the bandwidth of 5 GHz, and this is the absolute power accumulated through the bandwidth. If we are now going down with the bandwidth, we are going down also in level. If we go down more, now it's our choice to select a suitable bandwidth for our receiver in this particular application. So if I'm out in the desert Gobi, I can make the full bandwidth because there's nobody around nearby. If I go to the center of Munich, forget it. And that's the reason why the block diagrams of a complete radio may be significant different between application A and application B. It's basically the co-site scenario you have on the antenna level. And now a few numbers again, sorry for that. So we find our 97 dB again, which is the 5 GHz we had, and now we are going down relative to 5 GHz to 32 kHz in this example. And this is a relation of 52 dB. So we are going down from the 97, 52 dB, which means now when we are starting with a 7 dBm maximum going down, we will now be able to pick up minus 100 dBm compared to minus 48 dBm with a full bandwidth, because we are just reducing the picked up noise. And now the weak signals are coming out from the noise. That means full 5 GHz, minus 48 dBm. If you are going to 32 kHz, we have minus 100. And now our LNA on top, 24 dB gain, which leads to the minus 124 dBm signal we can see out from the noise. And now we want to have a signal to noise ratio, which says, okay, we have minus 124 dBm. Now we put, let's say, 10 dB on top. This is our signal to noise ratio. Now we have a receiver which is able to receive and demodulate and decode a signal with 10 dB signal to noise ratio with a level of minus 114 dBm with a bandwidth of 32 kHz. And with a minus 17 dBm on top, now we have a situation that we can have a level difference of 97 dB at the same time between our weak decoded signal and the strong interferer. And anything beyond that you want to achieve can be done with a block diagram. It cannot be done with the A to D converter alone, so you must provide some help. Put it into a block diagram with some pre-selectors in the front. We saw it from Hans' presentation, his filters between the A to D converter and the antenna. Or you say, okay, I put it in the superhead concept. The best superhead concept I built brought this 97 dB to 150, which is a military vehicle with a 50-watt radio and 10 dB antenna decoupling, while the radio is able to receive very weak signals. Now let's go to the digital to analog converter for the last 3-4 minutes. Here it's all about spurs and noise at the output. So if you're looking to the output spectrum of a digital to analog converter, you find everything. And this is an interesting situation. This is a situation where the customer is not willing to accept that you're delivering more than he has ordered. because you're delivering spurs and noise which is not intended, and you should get rid of that. So we have some noise here, you have some spurs, and they have different values in the data sheet, like spurious free dynamic range, dBc, compared to a carrier signal, or compared to the maximum signal the D to A converter is capable of. It's not exactly the same. The message here says, if you are varying this signal in level, it may happen that these signals are not changing in level. You have a socket of spurs available independent from the output. This picture you won't normally not find anymore. It's based on my very old designs, 35 years in the past already, where we have been dreaming about gigahertz sample rates. I made my first digital signal generator with 5 megahertz clocks with an EEPROM as a memory, providing 700 kilohertz output frequency as an intermediate frequency in a transmitter for a PLL, for controlling. But you must be aware there are some sampling artifacts even significantly higher than the clock rate, and if it's an advantage for you, just put a filter on these and pick out a particular spectral component if you don't need the complete tuning range, and then you have a very fine tunable frequency with good phase noise and probably fulfilling your concept if this is not on the antenna level, if it's part of the complete block diagram. Here, the same situation as for the analog to digital converters. This is a real block diagram, a real picture from a data sheet from Analog Devices 9177, sorry, and you see here the D to A converters we are talking about, but 90% more circuit around, otherwise you won't be able to use this device. You see here that NCO numerical controlled oscillator, the digital oscillator. You see here digital up conversion. Here, digital up conversion, some delays, some coarse tuning. Here you have some PLLs because you cannot go in, or you don't need to go in with 10 gigasamples. You can go in with significantly lower frequencies and activate a PLL on chip to provide these extremely high frequencies for sampling. And the result is amazing. If you look to this picture, these are some screenshots from this data sheet, and you see the spectral purity you can achieve with highly complex modulated signals, OFDM signals, whatever. It's absolutely amazing. And if you look closer, the close-in phase noise is normally, if you're forgetting the PLA and the chip inside and you would clock the DA converter directly, it's your own phase noise of your own clock. So if you are providing a high clocking frequencies to the device, and let's say you're taking out 1/10 of that frequency, in that case, this curve will be shifted by 20 dB lower to that curve you're providing as phase noise from your clock you have been generating somewhere else. Okay, right in time, exactly 30 minutes, and now I'm open for questions. Thank you very much.
Okay, bleeding edge technology. Any questions? Back there? Okay, hold on. Just a moment.
Wait for the microphone.
You have a question about the receive side ADC scenario. Aren't you ultimately limited by your processing gain by the SFDR of the ADC spec?
Yes, this is one of many limits. It's mainly the significant limit because it's a limit how deep you can dive into the noise. Because anyway, even if you have a reduced bandwidth, you won't gain a lot more dynamic range because the limit is reached already with that factor. Yes, you're absolutely right. Thanks.
More questions? Oh, really? No more questions about bleeding edge. Well, okay. Any question for me? Oh, yeah. Oh, yeah. Hold on.
How much does such a device cost if a radio amateur wants to buy a single one? Do you have any idea?
The cheapest one, some 10 euros, up to some 100 euros, just depending on the details in the data sheet. But But let's say you're investing 1,000 euro for a receiver with just a low noise amplifier around, providing 5 GHz bandwidth. I think the deal is not so bad, because you're getting rid of a lot of circuits around. One more question here.
Yeah, I've got a question regarding commercial receivers, and I read a report from an ICOM 9700, and I'm sure there are others, but they're also showing some spurious signals somewhere in between the maximum what you've shown and the minimum. There's something, and it wasn't further explained. Can you explain how that can come?
Can you repeat the last sentence?
I mean, how do the other signals, I mean, these spurious signals within the dynamic range come? I mean, that was from an English professor. He measured the 9700, and in the RL lab it was excellent, had excellent dynamic range, and he found out that within that range there was something which he couldn't explain.
Are we talking about the transmit spectrum or the receive spectrum? Receive spectrum. I have no idea what this guy did in measurement. My experience is that when we are talking about dynamic range this high, close to 100 dB and even more, it's very tricky to have the right test setup, because all the spurious of the signal generators in this scenario, the noise of the signal generators, are also very important. Probably it's based on the test setup he was using. I don't have any background information to that, but I had it several times in our production as well.
Mm-hmm. Okay, thanks.
Michael, you're still here.
Okay, thank you for the first sentence now. And I have to leave now for another talk. And if it is a long walk, I have to leave now. Thank you very much. Thank you for coming here. Thank you for staying with us. Hopefully for you, you had a successful day until now. And now I hand over to Marcus, and we will have some time to have a coffee break, I think.
Yeah, Michael, thanks for supporting the SDRA all those years. And yeah, we'll now have all the leftover talks. Right, any more questions? No more questions? I don't see any. From the chat? No more questions from the chat? No questions, okay. So, Thomas, thank you very much for giving us an insight in bleeding edge and the maxima, and how to push the limits even further. And yeah, do use those insights in your next projects. So it will be interesting to see where we're going, and we'll see that next year. Thanks very much.
Thank you very much.